Today we are going on to the second day of review for Chapter 5, and today's topic is inverse functions. So first thing, learning target. Students will review the concept of inverse functions algebraically and graphically, and you're going to find inverses of one-to-one functions. Now, before we go too far, I just want to do a quick little reminder here. This is a parabola. The question I'm going to ask is this a function? And I'm hoping that some of you are thinking, function, there's a test that we have. You guys have that vertical line test, meaning if I drew vertical lines on here, would it only hit the parabola once? And the answer is yes, it is a function. So now we're going to ask, is it a one-to-one function? And a one-to-one function is both a function that would pass that vertical line, and hopefully you guys remember, it would pass the horizontal line test. In this case, the parabola is not a one-to-one function because it hit the picture twice. So I'm just reminding you of some graphing things that you need to talk about. So, a function has an inverse if and only if it passes the horizontal line test and it is one-to-one. So this part right here, line test one-to-one, and we call this strictly monotonic function. And I might use monotonic, so I wanted to make sure that I at least highlight it, make sure that you guys understand what they are. So, in other words, the functions constantly increase or decrease. Two functions are inverses if. So, here is what you need to know. A, they are inverses if the domain of f equals the range of g, and the range of f equals the domain of g. Basically, the x's become y's, the y's become x's. So, if you look, here's my x value, my y value. Do you see in this case, the y came first, the x, they switched. And if every point switches, we know that they are inverse functions. Okay, so that is something to think about. Now, another thing that I want you to think about is B. This is going to be the mathematic or the algebra test that we are going to be looking at. And that is if f of f to the negative 1 of x equals x, and if f of negative 1 times x equals that. Okay, so I'm thinking that you guys are like, what the heck? So here it is. We're talking about composite functions. Do you remember the fog and the goth? If fog equals x, and it can only equal x, not x plus 1, not x squared, and g of f can equal x, then this test makes them one-to-one. So this is the test. Okay, so let's take a look at these first two functions. And I'm hoping that you kind of remember how to do this. So there's going to be two functions. There's going to be f of g of x. That's going to be one thing. And then I'm going to put a line down the paper, and we're going to also do g of f of x. So we're going to do fog and we're going to do goth. Now, to help color code these, or so you guys can see, every time I deal with f, I'm going to use green. Every time I deal with G, I'm going to use blue. So for this first one, I always like to rewrite them so you guys can get the idea of being nestled. F of G of x. So in the f function, wherever I see an x, I replace it with that whole function. So here we go. I am going to do my f of g of x. So it's going to equal, starts off with a 2. Oops, there's an x. So I am going to rewrite the cubed root of x plus 1 all over 2. And then that is my g taking the spot of the x, but then notice it's still cubed, and there's still a minus 1 behind it. So mathematically, I hope you guys get that the cube and the root will cancel each other out, and I am going to be left with 2 times x plus 1, divided by 2, subtract 1. And hopefully you guys can now see that those will cancel, and I'm left with x plus 1 minus 1. And guess what? Yay! It equaled x! Now, here's the kicker. They always don't equal the same thing, so you have to do the second part of the test. So for the second part of the test, in the g function, I am going to be putting the f. Okay, so in my g function, which is red, I'm going to have the cubed root of, and when I start to build my fraction, oh, there's an x. So now I need to put 2x cubed minus 1. That took the place of the x only, so now I have a plus 1 behind there and a 2. Okay, so let's do the math. I have the cubed root of 2x cubed. I hope that you guys see that the minus 1 and the plus 1 cancel each other out, and I'm left with it all over 2, which means I have the cubed root of x cubed, because these 2's would cancel each other out, which means I'm left with an x. Yay! And again, just because you guys hopefully can see that those would cancel out. And since these are both x's, since both equal x, they are inverses. And you need to kind of sum that up. You knew from the test that's what happened. Okay, so that is how to determine if two functions are derivatives. Now, pictorially, a function and its inverse are reflections over the line y equal x. Okay, so draw y equal x. That goes through quadrant 3, up through quadrant 1. It's like a 45-degree angle. So now its inverse, see how this part bows out? Oops, that bowed out, and see how that crosses? It would be a mirror image over. That is how you find or draw an inverse, and remember, this is the line y equal x. Okie doke. So we're almost done. Now, I'm going to start to mention trig functions because I know you guys hate them, but we've got to really look at our trig function. So, if I asked you about a sine wave, I'm hoping that you guys know a sine wave would look like this. Oops, kind of got bigger there, sorry about that. And I could draw it that way. You guys should know 0, you guys should know pi, you guys should know 2 pi. And if you can't remember where I'm getting these numbers from, if I do sine real quick, here's 0, at 0, at pi, and at 2 pi at 0. Up here at pi over 2, I would be at a y value of 1. Got it off of that. And when I'm at a pi value of 3 pi over 2, I would be at a y value of negative 1. Okay, so that is stuff that I kind of assume you know. Now, if I look at the entire sine, it's not 1-to-1. 1-to-1 means it's got to pass horizontal, it does, vertical it does, but horizontal it doesn't. So I have to find a region where it would pass. So in this example, we said if I looked at pi over 2 to 3 pi over 2, would this be a region where it would be considered 1-to-1 if I just look there? And yeah, it is 1-to-1 there. And there's lots of these regions. I might look from pi over 2, notice there's no number there, to negative pi over 2. That's the one I usually use. That region would be 1-to-1. If I looked at 3 pi over 2, and hopefully you guys can guess that this would be 5 pi over 2 when I finish that graph. It would be 1 to 1 there. So there's lots of regions where the sine graphs are 1 to 1. I just want you guys to start to think about this. Trig, inverse, we'll come back to that. So this last one, I like this problem because it does both. It asks you to find the inverse both graphically and analytically. So I'm going to draw a line, boom, on my paper. So graphically, what does this graph look like? Well, you guys better remember a square root function looks like this. With this 3 in here, it moves it 3 units, 1, 2, 3, to the right. And that 2 means instead of going up 1 over 1, I'm going to go up 2 over 1. So right about there. And my graph would look something like that. So now, if I wanted to graphically find the inverse, what line do I graph? Oh, on the front it told me to graph the line y equals x. Got it. And now it's inverse. Now notice, this is the point 3, 0. If it's an inverse, it goes to the point 0, 3. And it comes swooping in and swooping out. It's its mirror image. So the green right here would be considered my inverse. Okay, last thing, analytically. So to analytically find an inverse, it's not confirming like we did on the front. There are some steps, and I'm going to write each step in a color so you can see what it says. Step 1, I have to write the function with y, right? Function with y. Sorry that it looks kind of poopy. Okay, so instead of f of x, y equals square root 2x minus 3. Step 2, switch all x and y's. All x and y's. Okay, so to switch them, a y would become an x, a 2 stayed a 2, the x became a y, got that? Step 3, solve for y. Solve for y. Okay, so if I'm solving for y, first thing I'm going to have to do is square each side. So I'm going to get x squared would equal 2y minus 3. And then I'm going to get x squared plus 3 equals 2y. And from there, I'm going to get x squared plus 3 all divided by 2 would equal y. Okay, so that is my inverse function. Now, in order to talk about this inverse function, the one thing that I want to do is write the notation, and this would be raised to the -1 power. So I want you guys to see right here, this is inverse notation. You need to know that. Okay, the one thing that I'm guessing that some of you may need a little refresher in is how to graph some of these original functions. So if I just gave you the equation, oops, let's erase that, that's nasty. Let's go back to our pencil. If I gave you the function y equals square root of a x minus b plus c for this. You guys need to remember what moves a graph left and right. Left and right, oops, I forgot my parenthesis. Left and right movement is hooked directly onto the x. So the b value does that, but remember it's always in the opposite direction for that left-right movement. And what moves a graph up and down? Up and down would be the c value, and I just use that as is. And then what makes it stretch or compress? Stretch means it goes up faster. Compress means it's flat. Is the a value. And I am going to say, remember, fractions usually equal the flat or the compress. And then what would make it flip over the x-axis? If I had a negative sign right here, that would make it flip over that x-axis. So that should help you with some of the graphing for tonight. I hope this helps. It's just a whole bunch of information that you guys should recognize. Good luck.